Let's see if that somehow works. But the camera is not connected to the computer upstairs. So this particular performance will only be streamed and recorded per audio and not per video. Maybe that's good for everybody. All right. Yes. What did we do? We talked about Faraday rotation. That was the first important point of what we did last time. And we saw that a magnetized plasma is optically birefringent because left and right circularly polarized waves propagate with different speeds, different phase velocities through the plasma, and therefore linear polarization directions are going to rotate. Very important. I showed you that this is a very important means of diagnostics for astrophysical plasmas, such that you can infer the strength of the magnetic field by analyzing Faraday rotation. And you can analyze it because the degree of polarization of electromagnetic radiation depends on 1 over the frequency squared. So if you measure the polarization orientation at different frequencies, at different wavelengths, you will see different degrees of Faraday rotation, and therefore you can infer the absolute value of it. All right, and then we concluded that particular subject of propagation of electromagnetic waves through a plasma and continued with hydromagnetic waves. And what is this? These are the equivalent of sound waves in magnetized plasmas. And of course, we will have other waves than ordinary sound waves in a plasma because we have the magnetic field, and this acts back on the fluid flow, which acts back on the magnetic field through the induction equation. And then we followed the same procedure as every time when we analyzed the evolution of perturbations, namely, we collected the relevant equations, and these were divergence B equals 0, the magnetic induction equation, the continuity equation, and the Euler equation augmented by the magnetic force term that we have in that we had to add to the Euler equation. Then we decomposed all the quantities that appeared, namely density, the velocity field, the magnetic field, the pressure, into a background solution and a perturbation of it, and linearized the equation in the perturbations. That is, we threw away all terms that were of higher than first order in any of the perturbations, and we transformed into the rest frame of the plasma such that the 0th order for the velocity became 0. All right, then we had the usual linearized equations, and then we decomposed the perturbations into plane waves such that all the differential operators changed to algebraic operators. And so we got a set of linear algebraic equations for our perturbations. We then eliminated the density fluctuations, we eliminated the magnetic field fluctuations, and retained a single equation for the velocity fluctuations. And for that, or for those, we arrived at a matrix equation which looked like this. That's an S here. And this. All right, we had this matrix here times delta V equals 0. And we saw, yeah, I should say what the abbreviations were. So we said we introduced the Alfvén velocity which is the magnetic pressure, B0 squared divided by 4 pi, divided by the unperturbed density rho 0. That's the Alfvén velocity. And as usual, right, that's an energy density divided by a mass density, so that's a velocity squared. That's all fine. And Ck was omega divided by k. This is the frequency divided by the wave number of the sound waves. Okay, and we introduced an angle through the cosine. No, the cosine psi, I should say, was introduced as the scalar product between the magnetic field direction and the direction of the wave vector. So that is the angle between the magnetic field and the propagation direction of the sound waves. All right, that's where we were, and then we had a brief look at velocity perturbations. So that's number one, right? We saw that if we have velocity perturbations that point into z direction only, so these are transverse sound waves. Right? Usually you hear that sound waves are longitudinal. Some of them are, some of them are not. Here we have an example of sound waves that are transverse, because in order to set up this matrix, we chose the propagation direction parallel to the x-axis, right? Okay, so these are transverse waves, first of all, and then we saw that they obviously have to satisfy Ck equals plus or minus Ca times cosine psi. So this is their phase velocity, depends on the relative orientation between magnetic field and propagation direction. And if the magnetic field is perpendicular to the propagation direction, the sound waves go there, magnetic field points there, then the phase velocity is 0, and you have standing waves in the plasma. The characteristic speed is the Alfvén velocity. Now, if I write this somehow differently, omega divided by k is plus or minus Ca times b times k, right? If I replace the cosine psi by the scalar product and multiply k to the other side, so that I have omega equals plus or minus Ca b hat times k vector, then you see that the group velocity, d omega dk, that this is plus or minus the Alfvén velocity, but in the direction of the magnetic field. Right? So all physical information, energy, and so on are being transported along the magnetic field, and the phase is propagating into the direction of propagation, of course. Now, one more interesting thing is the following: we had used the continuity equation to eliminate delta rho over rho, and we saw that it was given by this, if I'm right. Yeah, that must be correct. Okay, and now we have the situation that the wave vector k is pointing into the x direction, but we have chosen a velocity perturbation in the z direction for our current analysis. So this means this is 0. So this means these Alfvén waves, which we are currently studying here, these Alfvén waves are not related to any density fluctuations. Right? So you have velocity fluctuations not associated with density fluctuations. In addition, if you remember, we had an equation that related delta B, the magnetic field fluctuation, to the velocity fluctuation. You can write this in the form I hope it's going to be correct what I'm writing now. That should be correct here. So now here again we have this matrix here, which multiplied with the vector delta V gives a scalar product between k hat and delta V, which is 0, like here. So this term doesn't contribute, but then you have, for this particular case of Alfvén waves with delta V proportional to Ez, sorry, we have 1 over Ck now plus cosine psi, which is this scalar product here, and then just delta V, which is in our case delta Vz, right? So you do have magnetic field fluctuations which should be opposite. So I probably have made a sign error here. There should be a minus sign here because the magnetic field fluctuations are always opposite to the velocity fluctuations along the z direction. So you do have magnetic field fluctuations associated with these Alfvén waves in the direction of the velocity fluctuations, perpendicular to the propagation direction of these waves. Propagation and the group velocity is pointing somewhere else. Okay, these are the Alfvén waves. Now, if we do not insist on having delta V proportional to the z-axis, so if we have a separate look at velocity perturbations now that have a Vx or Vy component but no Vz component, then I can reduce the propagation equation here to a two-dimensional matrix equation. And then the determinant, the subdeterminant of this 2 by 2 matrix here gives us the propagation condition. Now let's have a look at that. All right. So we will have to satisfy Ck square minus Cs square minus Ca square sine square psi times. I'm just calculating the determinant of this thing. Ck square minus Ca squared cosine square psi minus Ca to the 4th power sine square psi cosine square psi equals 0. Okay, that's our propagation condition. Now let's see what it says in detail. So you see one thing immediately. If you multiply this first product out, there's a term plus Ca to the 4th power sine square cosine square, which is going to be cancelled here. So let's have a look at the rest, which will be Ck to the 4th power. Then all the terms that go like Ck squared. There's one, which is Ca squared cosine square psi. There's another Ca squared sine square psi. So together they just give you a Ca squared. Then other terms that go quadratic with Ck square, just this Cs square here. Right, so this comes from here, and this completes all the terms that go like ck squared. And then you have, what do we have? We have one constant term, which comes from multiplying these two, right? So plus cs squared, ca squared, cosine squared psi. And I think that's it, right? So we have this and that, and this, and that, and this, and that will be cancelled. Okay, so this must be 0. So we have a quadratic equation in ck squared. So we can solve this here and get ca squared plus cs squared plus or minus the square root of ca squared plus cs squared squared minus 4 cs squared ca squared cosine squared psi. Yeah, that's a lot of different possibilities. In order to analyze what this means, let's have a look at specific orientation angles psi between the magnetic field and the wave propagation direction. So let us first set psi equals 0, so that cosine psi is 1. I should have written this over here. Good. If cosine psi is 1, you see that if you square this and you subtract 4cs squared ca squared, you get ca squared minus cs squared squared. So this, then we have ck squared plus or minus equals 1/2 ca squared plus cs squared plus or minus ca squared minus cs squared. Okay, and what is this? Well, for the plus sign, cs squared goes away and you get ca squared. For the minus sign, you get cs squared. Okay, so one of these modes that we now get are the ordinary sound waves. Right? Waves whose phase velocity is just plus or minus the ordinary sound speed. And there's another mode which has the Alfvén speed instead. If instead we say psi equals pi over 2, so that cosine psi equals 0, then we have ck plus or minus squared, ca squared plus cs squared plus or minus ca squared plus cs squared. Okay, so either for the plus mode, we get ca squared plus cs squared, an even higher sound speed, right, which is the square root of the squared sum of the Alfvén sound velocity, or 0. They're standing sound waves. And so on and so forth, right? What we have now looked at are just two particular cases for the orientation. Now, in the book here, wait a moment. You find a polar diagram. Which you should read in the following way. Right? Imagine you have a reference axis pointing towards the x direction, and then you have an angle between the x direction and the you just have the polar angle relative to the z direction, and then you see what the the phase velocities would be that you get from these two different branches for the dispersion relation here. Right? So the polar angle in this diagram is the psi here. And then you see you have a fast mode, a fast sound wave mode, and a slow sound wave mode, and the velocity changes with direction that you have. All right, and this is what I wanted to show you. So you have the Alfvén waves, you have fast hydromagnetic modes, you have slow hydromagnetic modes, and the phase velocities for these for these different types of sound wave can range from 0 to Ca squared plus Cs squared here. You have a full range of different excitation modes for the velocity fluctuations. Now, if you return to this situation here, or to this equation here, you see that if you have velocity fluctuations in x direction, those are also associated with density fluctuations. If you have them in y direction, those are not. Right? So you recover the usual longitudinal sound waves with a sound speed cs. And in addition, these waves are also connected with fluctuations in the magnetic field according to this equation here. All right, this is what I wanted to show you about hydromagnetic waves, right? To extend the analysis in hydrodynamics that led to the sound waves, and now you see the rich excitation possibilities for sound waves in a magnetized plasma. All right, do you have questions so far on this particular class of waves? Tim? So did you find anything? Why the camera doesn't work? It's working now. You're a hero. Thank you. All right, if you don't have any questions, I would like to return to one particular point that I skipped over, and that has to do with how you add gravity to the hydrodynamical equations. Remember, when we got there, I said, okay, if you want to add gravity to the hydrodynamical equations in the proper way, you remember that the hydrodynamical equations follow from vanishing 4 divergence of the energy momentum tensor, and then you replace the partial derivative by the covariant derivative, and then gravity is included. But then of course you need a gravitational field equation, which is the Einstein equation, and then you are in trouble. Right? Because then you have to solve the Einstein equations together with the hydrodynamical equations. All right, this would be the proper way, right? Even though it leads to trouble. But then we did something completely different. We said, okay, all we need in order to augment the Euler equation by gravitational force is that we have to add the gravitational force density on the right-hand side of the Euler equation. And then we said, okay, then we just have to add minus rho gradient phi to the Euler equation on the right-hand side, and we have taken gravity into account. All right. Yet another way, and this I didn't show you yet, and I wanted to return to that today, is that you set up, a stress energy tensor for the Newtonian gravitational field, and then add the gravitational interaction as all other terms in the Euler equation by a divergence of this stress energy tensor. We did that for the pressure, the kinetic energy, diffusion terms. We can also do this for gravity, and we could also do this for electrodynamics, by the way. All right, now I wanted to return to that, and on the way there, I wanted to show you another line of arguing, which is very, very useful in many occasions. And this is the so-called tensor-virial theorem. Tensor-virial theorem. Remember the ordinary virial theorem? It tells you that minus 2 times the kinetic energy is the potential energy. Yes. This is so often used in astrophysics. It requires equilibrium assumptions and so on, which nobody ever cares for. But a much more rigorous statement is the tensor-virial theorem, and I wanted to show this to you. Suppose you're interested not only in the mass distribution, so in the density, but also in the geometrical distribution of the density across a certain volume. When you set up the inertial tensor, it's not quite the inertial tensor that you know from classical mechanics, but almost. Right? You set up the inertial tensor in this way. Right? What does it do? It does not only integrate over the density, but it integrates over the density times the position information of the density. Okay, and now you want to know what is the total time derivative of this thing. Now don't get confused. You're integrating here over fixed positions x and a fixed volume in time. And if you now ask for the time derivative, you're asking how does the density change within this fixed volume. So these x's here, they are not x coordinates within the body flowing with it, but they are fixed positions in our coordinate system. So if I take the total time derivative, there's a single contribution to that, which comes from the partial time derivative of the rho here. All right. But the partial time derivative is connected to a divergence through the continuity equation. Aha. So I'm just using dt rho is divergence rho v, a negative divergence for rho v. Okay. I have a volume integral here. It contains a divergence. This cries out loud for Gauss' theorem. Wouldn't it be nice if I could write write this a little bit differently. That would be lovely, wouldn't it? Now, before we continue operating with these divergences of tensors under an integral, let me show you some pieces of notation that I'm going to use. So suppose you have a tensor product of two vectors and you want to apply its divergence. What do you actually do? By the way, first of all, you have to say on which of these dimensions the divergence is going to operate. So let's say this dj ai bj. Right, so the divergence would act on the second factor, on the second dimension of this tensor. Okay, so what is this? This would be dj ai times bj plus ai dj bj. Okay, if I return now to vector notation, this would be the tensor product of the nabla operator with A. If I wrote it this way, I would have diaj. I have the opposite, so this is a transpose here. Now, A times the vector B, and this is the vector A times the divergence of B. Okay? This is one thing. So, this is part of what I've used here. Now, I need one more thing, namely, I need the tensor product of the nabla operator with X. What is this? This is dixj. That's just the unit matrix. It's the unit matrix transposed, right? But who cares? Okay. So wait a moment. Yeah, okay. Now, obviously I've made an error, right? So here I'm applying the divergence only to the rho v vector here. Here I'm applying the divergence to the whole thing. I'm doing that because I want to get rid of this, right? By Gauss' theorem. But now, of course, I have to correct, and since I have a minus sign here, I have to add. What I get if I now apply divergence to the previous factors here. So this will be if I apply the divergence to this factor here, this will just give me a unit matrix here. And what will remain is just x cross rho v. And if you work out the indices and so on, you find that the rest will be rho v tensor x. Right? You get I'm lost in this. All right. So I'm ignoring this one by Gauss' theorem. And I say, all right, this is just d3x. Okay, that's a nice intermediate result. Now, I'm going to apply now another time derivative. And again, this will only lead to a partial time derivative of these current terms here. So once I'm there, I take this. Now I get this here. All right. But now I can use the vanishing divergence of the energy momentum tensor, because this here is C times d0 t 0I. Right? That's the time derivative of the 0I components of the energy momentum tensor. The C goes away because the T0I, if you look at it, contains rho CV. So this is minus dj Tij. This is minus the divergence of the stress energy tensor now. So I'm going to replace this by minus divergence of T bar. And remember, T bar was the stress energy tensor only. Right? The spatial component, the 3x3 matrix of the spatial component of the energy momentum tensor. All right. So therefore, I can conclude that this is minus integral d3x x times divergence of T bar plus divergence of T bar times x. And now I can play the same trick as before, right? Now I'm going to convert these divergence terms here into complete divergences and subtract the difference. So I get this. This will vanish, but of course now I have to correct. But what I have to correct for now is the unit matrix times the energy momentum tensor and the energy momentum tensor, stress energy tensor times the unit matrix. Right? So again, I'm starting with minus. If I correct, then I have to add. Now you use that nabla times nabla tensor x is just the unit matrix, and you find that this is just 2 times the volume integral over the stress energy tensor. This is written at a bad place of the board, but this is a very important result. And it tells you that the second time derivative of the inertial tensor, right, the acceleration of the inertial tensor, is just the volume integral of the stress energy tensor. All right. And with this, we stop for the moment. We have a break. And then we continue when I have wiped the board. All right, so here's the result that we got, right? If we take the second total time derivative of the inertial tensor, this turns out to be just 2 times the volume integral over the stress energy tensor. All right. What does it consist of? In ordinary hydrodynamics, you have this contribution from the ordered motion. You have this contribution from the unordered motion. So the first term is just the kinetic energy, the second, or 2 times it, the second just the pressure. But now, of course, if we want to take gravity into account, we will need some stress energy tensor for the gravitational field. Wherever we get this from, right? But this shows that you will have at least 3 contributions to the integral over the stress energy tensor. Namely, we'll have an integral over that. I'm calling this 2 times k. K is the kinetic energy tensor. Then you will get an integral over p d3x times the unit matrix. And we will get a tensor that I'm calling u. That's the volume integral over the gravitational stress energy tensor. Okay, so the k is I think it's pretty obvious why this is called the kinetic energy tensor. And u is the volume integral over the stress energy tensor of the gravitational field. Okay, so at the latest now we will have to specify what that should be. Okay. Here is one way of getting that. It's not the only one, but it is one. If you have any kind of field theory, for a field phi maybe, the Noether's theorems tell you that the energy momentum tensor is given by this expression here. So this just follows from symmetry, right? This is the consequence of Noether's theorem. L is the Lagrange density of the field theory. You take the derivative with respect to all the field momenta, d mu phi. You multiply with the field momenta, and you subtract the unit matrix times the Lagrange density. You know that from classical mechanics. Suppose you use the Lagrange function here instead of the Lagrange density. Then the only momentum you have is the q dot. Right? So you would take we only have one dimension here. Looks familiar, doesn't it? This is the one-dimensional version of what is above. Right? And this is just to connect this to what you know from classical mechanics. This is the Hamilton function in classical mechanics, and this is, if you wish, the Hamilton tensor of a field theory. That's the energy momentum tensor. Okay. Suppose now you take this Lagrange density for the gravitational field. This would be the Lagrange density for a free gravitational field if you said, okay, I'm adding a coupling term and you apply the Euler-Lagrange equations, you get the Poisson equation out if you neglect time derivatives of the gravitational potential. So that seems to be a good starting point for the Lagrange density for the free gravitational field, uncoupled to matter. If you now insert this up there, and then you take the space-space components of that tensor that you get this way, it looks like 1 over 4 pi g gradient phi tensor gradient phi minus 1/2 gradient phi squared times the unit matrix. Okay, if that looks strange to you, or you have doubts, look at the stress energy tensor of the free magnetic field. This would look like that. It's exactly the same, right? So let's stick with that and use that as the stress energy tensor for the gravitational field. Okay. Now we have to work this out with this expression over there. Let's see. This is what we have to do. Maybe things get easier if we do that. We saw this before, right? The tensor product of the gradient with x is the unit matrix. So let me just shift this in. But now I can write this as divergence. If I subtract what I did wrong, okay? And now the first term is the divergence integrated over space. So let's drop it. And we get as a first result, this is minus d3x x tensor, the divergence of this stress energy tensor. Okay, does that make anything easier? Well, let's see. If I take the divergence of the gravitational stress energy tensor as we have it over there, I would first have to take the divergence of that. Now, let me write this down in tensor notation. And if you wish, you can work this out with indices. The tensor of second derivatives of the potential, like the Hessian of the potential. Transposed actually, but yeah, it's symmetric. Times the gradient. This is when I act with divergence on this one. if I act with divergence on this one, I get a Laplacian of phi. Laplacian of phi. Now, we'll have to subtract the divergence applied to the unit matrix times this expression here. So this will be, if I first take the derivative of the 2 here, of the square, sorry. This will be this term. And again, I think it's pretty clear this way, but if you find it difficult, just write it down with indices. So you see the Hessian of the potential times the gradient of the potential drops out. But now we know from Poisson's equation that this is just 4 pi g rho. So this is, all in all, just rho times the gradient of phi. Remember, that's the term that we put by hand into the Euler equation. Now we have it systematically derived through a divergence of the gravitational stress energy tensor. And of course, right, this is just the negative gravitational force density. Okay, but this means that if we insert this into the equation for the U tensor, we get this the integral over d3x over x times tensor times rho times gradient of phi. This is a very useful formula for the gravitational potential energy tensor, which is due to Subramanian Chandrasekhar, and it's therefore also called the Chandrasekhar version of the potential energy tensor. Okay, good. Yes, in this way we could calculate that. Good, yeah. If you want to carry this out, then you need a specific model where you want to apply this to. All right, but let us now return to this tensor-virial theorem as we had it. Which said 1/2 times the second total time derivative of the inertial tensor is 2 times the kinetic tensor plus unit matrix times the volume integral of the pressure plus the potential energy tensor, for which we now have this additional formula. And let us assume that we look at a stable situation, and a situation in which the inertial tensor does not change anymore. And then we have, and then I take the trace of the whole thing. And then we get an expression for that replaces the classical virial theorem, which would just be a relation between the kinetic energy and the potential energy. And you recognize the factor of 2 again that you have in the ordinary virial theorem. But you see that the ordinary virial theorem lacks this contribution by the pressure because it does not distinguish between ordered and unordered kinetic energy. Okay. So here we have a stationary situation, and in this case, this relation holds. All right, now, if you take the trace of the kinetic energy tensor, you see that it's just rho over 2 times v squared. That's just the volume integral over the kinetic energy. Well, what else would you have expected? But now, if we take the trace of the potential energy tensor, what do we get? In this case, I'm going to return to the original definition of the tensor, so that I will have to take the trace of the gravitational stress energy tensor here. And this is very easy, right? Because now I have to take the trace of the first term here, which will be the gradient of phi squared. And I have to subtract the trace of this, which is 3/2 times the same. So the result is just -1/2 times the prefactor times the gradient squared. So this is going to be -1 over 8 pi g integral d3x gradient of phi squared. It looks easy enough, but it can be made easier. Again, by playing with divergences. Namely, how about that? If I take the divergence of this term here, that replaces this term, but of course has another contribution which I need to subtract, which would be phi times nabla square phi. But nabla square phi is 4 pi g rho. The divergence is integrated over the complete volume and goes away. So what remains is minus times minus plus. Then this is 4 pi g rho. This cancels, so I get this is 1/2 integral d3x rho times phi. It's so natural, right? It's just the integrated potential energy of rho in the gravitational potential phi divided by a factor of 2. All right. So in other words, this leads to 2 times the volume integral of rho half times v squared. That's from here. Plus 3 times the volume integral of the pressure plus 1/2 volume integral over rho phi I have the slight suspicion that I made a mistake here, but okay, rho phi, a sign error, okay. But this returns to this equation here, and notice we haven't made any specific assumption about the shape, or the velocity field, or the pressure, or the gravitational potential of that particular object that we're looking at. Right? It's a completely general expression. Okay, so that is the trace of the tensor-virial theorem under stationary conditions. Now let's use that in a very simple case. Let's assume that we have a spherical gas cloud, not moving at all. velocity equals 0. Density constant from 0 to radius r. It's not realistic, I understand, but okay. So then we would have rho equals rho 0, 0. This would be for inside, and this would be for the outside. We have v equals 0 because the whole thing is not supposed to move. And we suppose the gas cloud has a certain temperature. And of course, then the temperature will also be constant. So then the pressure, if it is an ideal gas, would be rho divided by m kBt. And m is the molecular mass, and it's the mass of a single particle. Okay. Then the first term just gives 0. And the next one, rho is constant, kBt is constant, m is constant. So we just have a volume integral over the density. That's the mass. So we then have 3 times capital M over small m times kBt. That's the pressure integral here. All right, now this one is a little more complicated, but of course if we have spherical symmetry, I can just factor 4 pi out. So that would be 1/2 a 4 pi rho. And then we have to integrate over r squared dr from 0 to r, because then the density goes to 0, r squared dr. Okay. Now we need the gravitational potential at radius r, which will be minus gm of r over r. Okay. But m of r we know, right? Because if the density is constant, then m of r is just 4 pi thirds times r cubed times the density. Okay. So this is supposed to be 0. So then we have the pressure integral. Now, minus 1/2 4 pi rho g times 4 pi over 3 times rho r cubed times r squared divided by r. So that's r to the 4th power dr, and that goes from 0 to r. All right. Now I can regroup terms a little bit. Let me write 3 times 4 pi over 3 squared. Okay? That covers this and that. Then I have rho squared. Then I have g. And the integral over r to the 4th gives me r, capital R to the 5th power divided by 5. I'm going to write r to the 6th power, to the power of 6 divided by 5r. So now you see these terms together with that one, this one I mean, is the mass squared. So this is just, the whole thing must be 0. So this is 3m over m kBt minus 3 over 10 g m squared over r. Now I can read off what the radius has to be. So then I can say that the radius has to be, 3 cancels out, m also cancels out. So we have gm over 10 times m divided by kBt. All right, this is meant to illustrate the power of such arguments. Right? We start from a very general relation here, and we see immediately what the properties of a system like that have to be, regardless of the simplicity of the problem. Right? But here you can immediately say, okay, the radius of the whole gas cloud has to relate to the mass and to the temperature in this way here. Let's play one more trick. Right? Let's say now we want the gas cloud to slightly rotate. Slightly, because I still want to operate in spherical symmetry. All right. Good. So I'm going. Let me write this underneath. Now I'm going to extend this example to consider a slowly rotating sphere. Of course, if it's rotating, it's not going to be a sphere, but an ellipsoid. Nonetheless, let's assume that the rotation is small enough for the whole thing to still be in approximate spherical symmetry. Then I will have a velocity field, a macroscopic velocity field, which will be omega cross r. I need the square of that in order to calculate the kinetic energy tensor. So that's going to be omega square r square sine square theta, where theta is the angle relative to the rotation axis. Right, so if I'm sitting on the rotation axis, of course, theta equals 0, and there will be no velocity, and so on. Okay, so then I can calculate what k is. I'm still assuming that the density will be constant throughout the object, so I can pull the rho out of the integral. Omega square, of course, is also constant throughout the object, so I will have to integrate over d3x r square sine square theta. Okay, of course, I'm going in spherical polar coordinates. Then from the phi integration, I get a factor of 2 pi. So I will have 2 pi rho omega squared divided by 2. And then I will have an integral over r to the power of 4 from the Jacobian and this factor of r squared. And I'm going to write the sine square as 1 over mu square. And this I have to integrate over d mu from -1 to +1. All right, the mu integral just gives 4/3. Right, integrating the 1 from -1 to +1 gives 2, so I have 2 minus 2/3, or 4/3. So it's going to be 4 pi over 3 again, times rho, times omega squared. And then r to the 5th power divided by 5. Okay, so this is 4 pi 3 rho times r cubed, that's the mass, m omega squared r squared divided by 5. Okay, and the rest I can use as usual, right, or as before. So now I know that 2/5, 2 because I have a factor of 2 in front of the kinetic energy tensor here, or of its trace right here. So I have 2 over 5 times m omega squared r squared. That's that. Now, this remains, right? This will be 3m over m kBt. All right. And the rest also remains, right? That's minus 3 over 10 g m squared over r. And now this has to be 0. Okay. So we can cancel one factor of mass. We can multiply the whole thing with r. So we get this equation here. Now it's third order in the radius, and this is not good because we can't solve this instantly. But we know that we have to assume slow rotation here. Otherwise, we couldn't operate in spherical symmetry. So this means that the radius cannot change by much. So let's say radius is going to be the previous radius plus a small correction. But then the previous radius needs to satisfy this equation, right? That's how we determined it. So if I insert this, I get 2 over 5 omega squared r0 cubed and no corrections, because omega squared is already very small. All right, plus 3 kBt over m times delta r. Because if I insert the r0 here, it's going to be to cancel with this one, by definition of the r0. So we are done. Okay, that's a linear equation now for the change in radius. Okay, so this means delta r is what? Minus, interestingly, 2 over 15 omega squared m over kBt times r0 cubed. The sphere is now smaller. Well, obviously, right? Because now the centrifugal force of the rotation plus the thermal pressure need to cancel the gravitational force. But we haven't changed the thermal pressure, so the gravitational force needs to be higher to keep everything together. And you achieve that by making the whole object smaller. Okay. From our previous result for r0, which I have hidden now, it's up there, gm over 10, m over kBt. I can isolate, or I can eliminate m over kBt. Right? So if I replace this m over kBt here by 10R0 divided by Gm, I get that 20 over 15 omega squared what do I get? 1 over Gm. So R0 to the 4th power divided by Gm. And 20 over 15, that's 4 over 3. Okay? All right. This is something that I wanted to show you. So, first of all, I wanted to return to our usual procedure that we applied in hydrodynamics, that we reduced hydrodynamics to vanishing divergences. And so I wanted to use one example to look at the energy momentum or stress energy tensor that we can assign to the gravitational field. I want to motivate one way of doing that, and that leads to the expression that we had. Then I wanted to use that in order to derive the tensor-virial theorem, because the virial theorem, first of all, is very often used in astrophysics, most of the time without motivation and completely wrongly. But nonetheless, it's being used. Right? People argue about virial equilibrium, even though there is no time for equilibrium. They neglect the pressure term in applying the virial theorem and so on. Nonetheless, it's being used. You should know about this. But then use the correct version, okay? And the complete version, maybe, which is the tensor-virial theorem as you see it up there. So it relates the second time derivative of the inertial tensor to all these other contributions. And you see, if you had any additional contributions to your hydrodynamical equations, you knew what to do, right? Because you know that on the right-hand side of the tensor-virial theorem, all we have is a volume integral of the stress energy tensor. And if you feel like adding other terms to the stress energy tensor, well, be my guest, right? But then you would need to complete the tensor-virial theorem accordingly. Okay, good. Then I wanted to show you these relations or these different expressions for the gravitational potential energy tensor, of which Chandrasekhar's version is one of the most famous. And you get all of this by shuffling divergences around, right? And making sure that you push the boundary of the volume that you integrate over to regions where the density is so low that you can neglect boundary terms. All right, if you do all that, then you can write down a scalar version of the virial theorem under stationary conditions, which sits in the box here, and which shows you very clearly that there is a pressure term in the virial theorem, which is most often forgotten or neglected. Poor thing. All right, and once we arrived there, I wanted to show you with two examples what you can now do with that, right, under simple or less simple conditions. All right, do you have questions? Then I wish you a Merry Christmas and a good start into a Happy New Year. And the lecture will start again on January 8th, Monday, January 8th, 9 o'clock. Thank you very much.